All right, so we're going to discuss concentrations of solutions today. We're going to go over several types of concentrations, and again, we'll go back to the Dr. Collins packet and work through his little study packet, and then we'll do some example problems, and then we'll look at some actual PCAT problems to emphasize all of these different concentration units that we'll be dealing with. So let's look at percent by mass. Essentially, percent by mass will be the mass of solute divided by the mass of the solution times 100%. So let me go ahead and formally define that. Percent mass. So this is commonly called M/M. So we'll have masses of both the solute and of the solution. We could do a mass volume, or we do the mass of the solute and the volume of the solution. We can also do volume. Mass is going to be by far and away the most common one that you would encounter of the three that I've just described. So we'll have the mass of the solute. Remember, the solute is the minority component of the solution. It doesn't mean it's the solid. It could be liquid, it could be gas, divided by the mass of the solution. That's the solvent plus the solute, times 100. And of course, our unit will be a percent, so I'm going to include that on our definition. So let's look at a problem. We have a solution that's 10% glucose by mass. How much glucose will we have in 800 grams of solution? So if we have 800 grams of solution, and for every 100 grams of solution, I have 10 grams of glucose. Essentially, I'm going to multiply 800 by 0.1, which means I will have 80 grams of glucose. Nice, simple, one-step solution. Eighty grams of glucose. Let's look at another one now. What volume of a 5% glucose solution would contain 20 grams of glucose? So when we're being asked for a volume, we need to make the assumption, in the absence of any other data, that the density is 1 gram per milliliter. Of course, it won't be 1 gram per milliliter, but it'll be very close to that because it's a very dilute solution. It's only a 5% glucose solution. These types of questions are much more common on the PCAT because as a pharmacist, you're going to have to deal with concentration of solutions much more often than if you're a dentist or even a physician. So these are almost exclusive to the PCAT. I have a 5% solution, and if I look at the rest of the problem, I'm going to have 20 grams of glucose over X. And of course, we know that this is times 100%. So I have 5X equals 2,000. X, of course, will be 2,000 divided by 5. Let's start using some common sense for estimating this. 2,000 divided by 10 would be 200. This is going to be twice 200, so this would be 400. 400 grams of solution would be 400 milliliters of solution, which would be our final answer. In other words, 20 over 400 times 100% should be equal to 5. So that means 2,000 over 400 should be equal to 5. I could cancel 2 zeros from the numerator, 2 from the denominator, and 20 over 4 indeed is 5. So I know my answer now makes sense. Let's now look at 9.4. We're asked how many milligrams of solute are present in 250 milliliters of a 2% solution. So this refers to weight volume percent mass. So we have a 2% weight by volume. So 2 equals, we know that the volume is 250 milliliters. We know we have to multiply by 100. And we're trying to find out what the mass will be in milligrams. Typically, we are going to use units of a milligram per milliliter. So actually, this is going to give us our answer in grams. And then we'll just convert it to milligrams. I'd like to take this opportunity to endorse the Central Library because they're full of frickin' idiots. Okay, so we have 500 equals 100x. 5 equals x. So the question asks us to present the mass of the solute in milligrams, so we'd want to multiply by 1,000. So just very quickly, the dimensional analysis will be 10 to the third milligrams is equivalent to 1 gram. So we'll have 5,000 milligrams. So remember, the definition is going to be mass of solute. That mass is given in grams, divided by volume of solution. That volume is given in milliliters. This is per the definition. times 100. And again, this is a percent, so we'll tag the percent and integrate it into our equation. This is mass volume percent. Now, let's discuss molarity. Let's discuss molality. Let's discuss normality. Let's discuss mole fraction. And this is going to bring us into a discussion of colligative properties. So molarity is the one that we learn really first in a general chemistry sequence. We know that molarity, which is, its unit is a capital M, is moles of solute divided by liters of solution. Now, those units are immutable. The problem with molarity is that molarity is temperature dependent. Let's go back to gas laws for a moment. We know that volume and temperature are directly proportional. That's Charles' law. When I increase the temperature, I increase the volume. According to this equation, I'll decrease the molarity. So the molarity is not constant over a range of temperatures. So when we are doing an experiment where temperature change is a part of the experiment, two great examples: the elevation of boiling point, the depression of freezing point. We can't use molarity as our concentration unit. We have to use molality, because molality, or lowercase m, is moles of solute. Notice that's exactly the same as molarity, divided by kilograms of solvent. These two are typically converted into one another when the density is known. So I need the density to convert these two. You're probably not real likely to get this kind of problem, but just so that we hedge our bets a little bit, we can convert between these two. Normality is almost always reserved for acids and bases, and it's really not used that much any longer. So normality, capital N, is equal to equivalence per liter of solution. Let's use a quick example to illustrate the difference between normality and molarity. If I have a 2.0 molar solution of H2SO4, I have a 4.0 normal solution of acid, because I have two ionizable protons. So I would multiply the 2 in the 2 molar by the 2 ionizable protons. We don't see this a lot anymore, but just in case they try to get sneaky and slide it into the test, let's be prepared for that. Now, we use molality for the elevation of boiling point and the depression of freezing point. So I'm going to make some additional notes. We use molarity for osmotic pressure. We're going to be dealing with these colligative properties in just a few minutes when I talk about them more formally. We use molality for the elevation of boiling point, for the depression of freezing point. And of course, the colligative property for osmotic pressure is that osmotic pressure will increase as I add particles. Mole fraction is simply a mole percent. If I have a gas A, a gas B, a gas C, the mole fraction of A would be moles of A divided by the total number of moles in the system. This is reserved for gases. It can at some point be applied to aqueous solutions, and we will use this for the depression of vapor pressure. Now, what I'd like to do are some examples with these different concentration units. And then I would like to conclude this podcast by introducing specifically the colligative properties in a conceptual manner and also the colligative properties in a more mathematical manner. So let's look at some example problems that deal with molarity. So in portion 9.1, we are asked how many moles of solute are contained in 750 milliliters of a 4 molar solution. So again, I would always begin with our basic equation for molarity. Molarity is moles of solute over liters of solution. The units are critical here. I have a 4 molar solution. I don't know how many moles I have, but I know that I have 750 milliliters. That is 0.75 liters. Now remember, molarity is moles per liter, so I can write 4 moles per liter. Of course, really what I'm doing is I'm cross multiplying times 0.75 liters. Notice the liters will cancel. 3/4 of 4 is 3. So I have 3 moles of solute. Nice, simple, one-step dimensional analysis problem. Let's also, let me find it. Nine two. A solution is prepared by dissolving 60 grams of NaOH in enough water to give a total volume of 500 milliliters. What's the molarity of NaOH? This one's a pretty simple, just application of the definition. So we have 60 grams of NaOH. Now we've dealt with NaOH a couple of times now. NaOH has a formula mass. Notice I didn't say a molecular mass because it's ionic. Sodium is 23, oxygen is 16, hydrogen is 1. It is 40 grams per mole. In the problem, we have 60 grams of NaOH. I need to convert this to moles. There are 40 grams of NaOH in 1 mole of NaOH. This is just like doing a very basic stoichiometry conversion. Nothing fancy. I now have my numerator in terms of moles of solute. Going back to our original definition, moles of solute over liters of solution. Furthermore, I'm given the fundamental fact that I have 500 milliliters of solution. That's 1/2 of a liter. 0.5 liters of solution. Notice I want liters of solution in my denominator. I have all the units I need. 60 divided by 40 is 1.5. 1.5 divided by 0.5 is the same as 1.5 times 2. That is 3 molar. So the answer to 9.2 is 3 molar. Okay, now let's talk about a simple molality calculation. We have a solution that's prepared by dissolving 60 grams of glucose in 500 grams of water. So 60 grams of glucose. Now glucose is another one of those molar masses I just think you should know. It's 180 grams per mole. It's C6H12O6, which reminds me of one of the greatest signs I've ever seen in my life. I stole it from the University of Memphis. You can call them if you want to and tell them about it. For a sweet time, called C6H12O6. All right, so 6 carbons, you got 6 times 12. That, of course, is 72. 12 hydrogens, 12 times 1 is 12. 6 oxygens, 6 times 16 is 96. 84 and 96 adds up to 180. They ask about glucose quite a bit on the PCAT, quite a bit on the DAT, so you might as well, I don't want to say memorize, but we use it so much it shouldn't be that big of a deal to simply recall that when needed. So I have 180 grams of glucose in 1 mole of glucose. So 60 over 180 is 1/3. And then we have 0.500 kilograms of solvent. I like to go back to the problem, just double check I have my numbers correct. 60 grams of glucose and 500 grams of water. So that's 1/3 divided by 1/2. That is 2/3 molal. 0.667 molal. Now let's talk about mole fraction and do an example mole fraction calculation. So let's say I have 2 components, A and B. The mole fraction of A, which by the way is abbreviated as capital Chi with a subscript A. It is the moles of A over the total number of moles. I represent that with a Riemann sum of all the moles in the system. So in our example problem, which is 9.7, we have 0.5 moles of solute and 4.5 moles of solvent. So I'm going to call the solute A. So the mole fraction of the solute, which will be a lowercase s, is equal to 0.5 moles. Now here's where you have to be careful. A lot of people will just put 4.5 in the denominator. It's not 4.5, it's 5. Because you have 0.5 of the solute and 4.5 of the solvent. Therefore, the mole fraction is going to be 0.1. Then for the solvent, that part's easy. I'm just going to subtract 0.1 from 1. And I get 0.9. That means 10% of all of the moles in this system are due to the solute, while 90% are due to the solvent. Now, a really nice application of this is alcohol. If one were to go buy wild turkey, they would find that wild turkey is called 86 proof. That means it is 43% volume alcohol or ethanol. What would be the mole fraction of this? Let's assume we have 100 milliliters, or we have 100 grams, so 43 grams would be due to the ethanol, which has a molar mass of 46. This is very close to 1 mole. A little less than 1 mole, but very close to 1 mole. So let's call it 0.97 moles. And even though this isn't a PCAP problem, I think it's an interesting real-world application problem, so I'm going to use my trusty calculator app on my iPhone. And actually, it's not 0.97, it's 0.935. So let's fix that. .935 moles of ethanol, which means I have 57 grams of water. The problem is water is only 18 grams per mole. So I have over 3 moles. In fact, this is going to be probably 3.167. 57 divided by 18. 3.17 moles of H2O. So what's the mole percent of ethanol? It's 0.935 over 3.17 plus 0.935, 4.102. Do a simple math calculation. The mole percent of alcohol is 22.8%. So next time you're out partying and someone says, "Oh, there's a wild turkey, it's 43% alcohol," you may inform them that the mole percent is only 22.8 and they therefore are pathetically weak.